All right, so we looked at the integrated first rate laws. Remember, integrated rate laws are looking at rates as a function of time, not just of concentration. So what we're going to do now is we're going to look at second order, and then we're also going to look at the idea of half-lives, which we get to talk about more in the nuclear chapter. All right, so here we are looking at the integrated second order reactions. Now, with second order reactions, we actually have two different possibilities of a type of reaction. It might be one where the rate is going to be two different reactants. So maybe A times B, and both of them are to the first order, so the overall is second order. That's a possibility, but it's not what we're going to be looking at, so I'm going to X that out. We're going to look at the example where you just have one reactant that the rate is dependent on. It doesn't mean it's the only reactant, but it's the only one that the rate's dependent on. And this one happens to have an order of 2, so it's a second order. Now, a couple things to note. Here's the two equations you need. I don't have an example in the notes for this, but be sure to write these on your cheat sheet card, because you'll probably see them on a homework, on a worksheet, and maybe on the test, who knows. Excuse me. These particular equations are kind of a pain because you have a fraction in there. So it's a little bit harder to work with, or a little more, I don't want to say harder, it's just a little bit more mathy, kind of complicated math than some of the others. On this one, also note that a plot of 1 over the concentration versus time produces a straight line. We want to make sure to make notes of where those straight lines are going to occur. So here's just a reminder. Oh yeah, if you take 1 over the concentration versus time, that's going to give you the straight line. And the slope of it is actually your rate constant K, which is kind of fun. Sometimes you can do problems where all that gets brought into that play, and so you can find all sorts of cool connections between your equations. And then we move on to this idea of half-lives. So sometimes this is called T1/2 on the bottom. And what a half-life is this is the time it takes for half of your sample to disappear. So the time it takes for half of your reactant to disappear. This does depend on the order of the reaction. The first orders are probably the easiest, and they're probably the ones that you're going to deal with most often. So down here, this is your first order reaction for half-lives. This one, it turns out, it's independent of concentration. So it doesn't matter if you have a big sample or a little sample, this rate is always going to stay the same. And the rate is only dependent on your K. So you have 0.693 divided by K, whatever the K is. And remember, that changes for the reaction that you're looking at, and it can also change for the temperature that you're looking at. Radioactive decay is an example of this, and we're actually going to get to talk a lot more about radioactive decay later on. So we kind of introduced that idea here, but you actually get to see it a lot more later on. So you'll see an example here in just a few minutes. So the second order half-lives, they do depend on concentration, on the original concentration. And so for every half-life that you have, it's a lot longer than the previous half-life. I know that doesn't make much sense yet, but the first half of the sample that disappears fairly quickly. The next half, so when you go down to 25%, that part, even though it's less material that is going to decay, it's a lot slower. And then the next half-life is even slower than that. There's no constant time on this. This one, we have an equation. Just make sure to write down that equation and make a note that this is for your second order half-lives. This is one where, and it would tell you, hey, you have a second order reaction. What's the half-life, or what happens in this particular case? So here's some half-life problems. The first one looks really, really big and scary, but it's really not. But you do have to understand some of the concepts behind it. So let's read through it, and then I'll show you what to do on the next slide. It says one of the most dangerous radioactive isotopes released in nuclear explosions or accidents is iodine-131, which concentrates in the thyroid gland. Okay, so that's all good and dandy and gives you some information, but you really don't need that for the problem. He goes on, the half-life of iodine-131 is 8 days. Okay, that's important. So what this is saying is that your half-life, so T1 half, is 8 days. Now, just as a little side note, for radioactive decays, your half-lives have a huge range. They could be anywhere from seconds or even milliseconds up to millions or billions of years. So there's a huge wide variety, as we're going to find out in a later chapter. This one says, what fraction of the initial iodine-131 would be present if the patient in a patient after 24 days if none of it were eliminated through natural body processes. So we're trying to get out up to 24 days. Let me show you what this would look like in a graph form and help you out just a little bit on this next slide. All right, so here's our next slide, and we actually have this graphed. And so what you'll find for half-lives for your first order is we always have this curve that's going to show up. The high point is going to be your initial concentration, or 100%, depending on how it's written. And then after every half-life, this amount goes down by half of your sample is now gone. And then what will happen over here on the right is we'll never actually reach the x-axis. It stays just above it. Half-lives are kind of weird. So let's look at this one. This one looks in particular at iodine-131. I want to just give you some ideas on this. I'm giving you a little too much information than what you need, but I think that you'll find it useful. So let's see here. We're going to look at the number of half-lives. We're going to look at the number of days. And then we're going to look at the percent and the fraction. So when you first start off, you have 100% of your sample, or 1 over 1, however you want to think of it. And then what we're going to do is we're going to look to see what happens after each half-life. So after the first half-life, now for iodine-131, that's 8 days. So remember, that is dependent on what compound it is that you're looking at. Half of your sample has decayed. Now, if we're looking at a nuclear decay, that actually means that it changes to another element. It's crazy to think about. Now, if we look at the fraction, that means that 1/2 of your sample is gone. It's decayed. It's changed to something else. Now, let's say we go through another half-life. That means 8 more days have passed. We're 16 days after we started. Half of this 50% has decayed. So half of 50 is 25%. Half of a half is a fourth. And then we get to keep going. After another half-life, that means another 8 days has gone by. We're 24 days after we started. We're down to 12.5%. And that gives us, what is that, 1/8 of a fraction of the initial. Now, this is actually where you can stop with the problem, because the problem says what fraction of the initial would be left, and you'd be left with 1/8 of what you started with. But let's go a little bit further. I want to do 1 or 2 more just to make sure that you understand the concept. So 4 half-lives, that's going to be 32 days after you started. You're down to 6.25%, or 1/16. Let's try it again. If you go 5 half-lives, you're at 40 days after the original. Your percent drops to 3.125%. The fraction would be half of that, which would be 1/32. And you can keep going. Now, normally with half-lives, we look up to 10 half-lives. 10 half-lives gives you 0.1% of your original, and it's actually 10 times whatever that half-life originally was. So for this example, if you went down to 10 half-lives, it would be 80 days after your original. You'd have 0.1%, and on the fraction it's like 1 over 1056 or some crazy number like that. So hopefully that makes it a little clearer. Again, we're going to revisit this idea of half-lives when we get to nuclear decay later on. And here is another half-lives type problem. So it says the reaction, it gives you the reaction, has the rate log rate equals K concentration HI squared. Now, because this is squared right here, we know that this is a second order reaction. Remember, you have to, you can't predict it based on the actual equation, well, until we get to Friday's lecture, but this one actually tells you it's a second order. This tells you what K is. The temperature we're not going to use, but remember the temperature, K is dependent on the temperature. Then it says what is the half-life for this reaction at this temp when the initial concentration, so this is your initial concentration. Oops, I did the wrong letter there. Let's try this again. This is your initial concentration. There we go. Is 0.05 molar. Now, because we know this is a second order reaction, we know we're looking for the half-life. All you have to do is go and find the equation that works. So this is going to be 1 over K times the concentration of B with the initial concentration. So in this case, we have 1 over K is 0.079. If we want to look at our units, it's going to be liters over moles second. And then we multiply that by the initial concentration, which in this case is 0.05 big M, or moles per liter. That means the moles and the liter cancel. It's going to leave you with seconds at the very end. Now on this one, do be careful because you have, it's all on the bottom, so it makes it just a little bit difficult to do your math with. Not bad, it's just something to be aware of. And so this one is going to equal 253 seconds. Hopefully that is the answer that you got. And I have to go see what my little one's hollering about. So I will catch you for the next lecture part.